Next, we'll look at one of our conditional rules, conditional elimination. What does this rule do? It tells us that if a conditional and its antecedent appear in two lines of our proof, we may add the consequent on a new line. The rule conditional elimination is also known as modus ponens. So you may hear that phrase used. Again, let's look at the schematic to see the structure of the rule. On line M, we have a sentence, if A, then B. And on another line N, we have the antecedent, A. The conditional elimination rule then allows us to add the consequent as a separate sentence on a new line. And we justify this new line by the rule conditional elimination and the lines M and N on which we found the original conditional and the line on which we found the antecedent. So note carefully that you must have both the conditional and its antecedent in order to infer the consequent on a new line of the proof. In the example to the right, we see parts of a proof where the sentence, if not R, then T, appears on line 6, and then the antecedent, not R, appears on line 8. Those two sentences fulfill our requirement for applying conditional elimination, which was applied here on line 11. That rule allows us to add the consequent T as a new sentence on this new line 11. And again, we have our justification. The introduction of this new sentence without a conditional in it, hence conditional elimination, is justified by this conditional elimination rule, shortened arrow E, and the lines 6 and 8 where the conditional and its antecedent initially appeared. For this rule, the idea is that conditional statements tell you what will be the case if a certain condition holds. So this rule says if we can infer a conditional and we can infer an antecedent, then the condition, so this rule tells you that if we can infer the conditional and infer its antecedent, the condition, then it makes sense that the consequent follows. The conditional holds, the condition holds, so what follows from that condition also can be on your proof. The biconditional elimination rule is very similar to the conditional elimination rule. The only difference is that it's a biconditional, so the conditions go in two directions, not just one. So how does the rule go? If you see a biconditional and you see either of its component sentences in two separate lines of your proof, then you can add the other component sentence on a new line. So here we don't have a particular example, but we have the two separate schematics for biconditional elimination. The left schematic is one where we assume the left side of the biconditional A, and in the right schematic, we assume the right side of the biconditional B. The rule for biconditional elimination allows you to introduce the other side of the biconditional on a new line. And then you justify it as usual with the abbreviated rule name, and then the lines on which the biconditional and the relevant component sentence appeared. Remember, the biconditional is just an abbreviation for a conjunction of both directions of a conditional. So the same logic that justifies conditional elimination also justifies biconditional elimination. It's just that for biconditional elimination, we have both directions, not just one. You'll notice that we're moving on to disjunction introduction. We're skipping the conditional and biconditional introduction rules. And that's because those rules require us to introduce a new aspect of our proof techniques. So we'll look at those rules as well as disjunction elimination in the next video, and we'll go on to disjunction introduction for now. This rule says that for any sentence that appears on a line of our proof, we may add the disjunction of that sentence and any other sentence of truth functional logic on a new line. So here's our schematic. When we have a sentence A on line M, the disjunction introduction rule allows us to add the disjunction of A and any sentence of TFL B on some new line. And then we have our justification, or I for disjunction introduction, and the line M on which we found the original sentence. And we'll look at our example here. P or Q appears on line 5. The disjunction introduction rule allows us to add any disjunction with P or Q as one of the disjuncts. In this case, we added P or Q or R. The introduction of this new sentence with the new disjunction symbol is justified by the disjunction introduction rule and line 5 where the original sentence appeared. Note that the original sentence in line 5, I happen to choose a disjunction here. But as our metalinguistic variable shows, it could have been any sentence of truth functional logic with any connective in it, or no connective. So could the other disjunct. We happen to add R, but we could have added a complex disjunct like if not S, then T. The idea behind this rule is that if we can show some sentence follows from our assumption, then we should know that that sentence or any other sentence will also follow from our assumptions. After all, remember that a disjunction is true as long as one of the disjuncts is true. So if we can prove one of the disjuncts given our assumptions, that's enough to accept any disjunction that has that sentence as one of its disjuncts. Negation elimination is the last of the rules we'll cover in this video. This rule works a little differently from our other elimination rules. We don't exactly have a rule for dropping a negation symbol out of a sentence. Instead, negation elimination depends on showing that the assumptions of an argument lead to a contradiction. So the way negation elimination works is as follows. If you see a sentence and its negation as two lines of a proof, you can state a contradiction on a new line. Let's look at what that means in terms of the schematics. The basic structure of this rule requires that not A and its positive A both appear on separate lines of the proof, here M and N. These two sentences contradict each other. For example, it can't be the case that it's not raining, the negated sentence, and it's raining, the positive sentence. This upside down T symbol that we see on a new line is a way of signaling that the lines of our proof have given rise to a contradiction. So you conclude, if we see not A and A, we have a contradiction in our proof. And we write that with this upside down T and justify it with the negation elimination rule and the lines M and N on which the negation and the positive sentence appear. So let's look again at an example. On line 8, we find not Q. On line 10, we derive not Q. Because sentence 8 is the negation of sentence 10, we can apply our negation elimination rule and then state a contradiction on on some subsequent line, here line 12. So as usual, our new line is justified by reference to the rule and the lines on which the negated sentence and the original sentence appear. For now, we're just going to introduce the idea that a sentence and its negation lead to a contradiction. But in the next lesson video, we'll actually look at the notion of an indirect proof, and that will allow us to make further inferences when our rules generate one of these contradictions. With those 7 rules, we can actually construct some simple proofs of validity for sentences of truth functional logic. But in the next video, we'll look at a more complex technique that we need to construct additional proofs.